Hello students, welcome. Mr. Hinkle here. Today, igneous rocks. Igneous rocks are cool. Igneous rocks are rocks that form from molten material, liquid, hot magma, or lava on the surface. And we see them exposed in mountain ranges. Here we see igneous dikes and a hornblende gabbro. Those are two different types of igneous rocks. This is in the eastern Sierra Nevadas. So we're getting into rock types and importance and all of that, but I think it's important to remember that mountains are made of rocks. Our Earth is made of rocks. One of the primary rock types that our Earth is made of, one of three, is igneous rocks. So let's get into it. These rocks are created from the cooling and solidification of molten material. That means that if we have the surface, we're just going to draw in a little volcano like so. Molten material underneath the surface is called magma. When this magma freezes, it actually turns into rock. And the rock becomes a set of interlocking crystals. And so when we're identifying rocks and we pick up a rock and we say, oh, look at these crystals that look like they've all grown together, this is an igneous rock. Now, as always, our story gets more complex than that. So we've got magma underneath the surface that forms igneous intrusive rock and lava on the surface that forms igneous extrusive rock. So here is lava on the surface. So the material here is molten. It is melted rock. Same ingredients, but melted, a different phase. Underneath the surface, it's magma. On the surface, it is lava. Lava is on the surface, magma is under the surface, giving us, and here's what I'm showing, two different types of rocks. We've got extrusive igneous rock that crystallizes from lava on the surface, and intrusive igneous rock that crystallizes from magma under the surface. In general, the cooling rate is much slower subsurface, which gives us larger crystals. The cooling rate is much faster on the surface, which gives us smaller crystals, less time for the crystals to grow large. When we're looking at identifying igneous rocks, we're going to identify two things, texture and composition. Texture is going to be the physical characteristics of the minerals indicating cooling history, and the composition is going to be the mineralogy and the specific chemical composition. Are there iron? Are there magnesium, silicones, oxygens? We can actually identify maybe not the actual percentages, but the relative abundance of these by looking at the rocks. We'll talk about that today. So, texture. Phaneritic. This is granite. It is an igneous intrusive rock, meaning it formed from magma inside of the earth, and you can see the crystals are grown together. This texture is called phaneritic, coarse-grained. This rock is basalt. It is what's called aphanitic. You can't really see the crystals. They're very, very small. You can see that there are tiny crystals growing together, but it indicates rapid cooling at the surface, igneous extrusive rock with an aphanitic texture. Porphyritic. I don't have a porphyritic with me at hand, but basically that indicates you had some slow cooling and then rapid cooling, where there's one crystal that is large enough to see inside of an aphanitic matrix. Oh, getting to processes of how these rocks are actually cooling, indicating depositional environments. Continuing on. Pegmatitic. Very large crystals. You can see that crystal is almost as large as my thumb. These happen in veins or masses. Sometimes there's water involved. There are certain conditions that lead to very large crystals, giving us the rock pegmatite and a pegmatitic texture. Vesicular. Vesicles are air bubbles inside of the rock. So it is volatiles or gases that are releasing at the time of formation that get trapped inside of the solidifying rock. You get two main types. You get scoria when you have dark colored volcanic rock, as we see. That's what I'm holding here. Pumice. Pumice stone, like, yeah, you scrub the calluses on your feet. That's an earth material. Pretty awesome. Pumice is also an igneous rock with vesicular texture. Let's keep going. Glassy. Obsidian. It's smooth, it's pretty, it's been used for a long time as a stone tool. Well, igneous rock with the vesicular texture actually doesn't have a chemical composition. There's no actual minerals in here. This is called volcanic glass, and here we can see some big deposits of it. Indicates very rapid cooling where the crystals didn't have enough time to actually form. The ions didn't have time to align into their crystal lattice or their crystalline structure. Last but not least, pyroclastic. So notice the shape of this. Go long. This is called a volcanic bomb, and it forms as volcano is erupting, and it spews lava, and it spins, and it cools in the air before it lands, forming a rock of material from fragments that are ejected from a volcano. Pretty cool, huh? So, pyroclastic texture is formed of fragments called tephra, and then when these tephra fragments deposit, the rock is called tuff, usually a welded tuff or a volcanic tuff. So, these are our textures for igneous rocks. And I love this image because these textures show us, where did this rock form? Texture indicates geologic history, the conditions at formation, the cooling rate, the location that it originated from. So I pick up this rock and I go, phaneritic coarse grain temperature, composed of mineral grains that can be identified without a microscope, tells me that it formed in a magma chamber or a pluton deep underneath the surface of the earth. Great. That is igneous rock texture. Now, composition. Composition is really looking at the amount of silicon and oxygen, the two most abundant elements in Earth's crust. And they form the silicon-oxygen tetrahedron that is the basis of the silicate mineral group, 90% of minerals on Earth's surface. So there's a lot of silica. Now, iron and magnesium also are key players in thinking about the composition of different igneous rocks. We have felsic and mafic. So we will use granite and basalt. Felsic and mafic. And really what I'm saying is this rock is light colored and this rock is dark colored. And there's a spectrum in between based on all of the unique properties that make up these individual rock types. This has implications because different elements have weight, different elements that compose these different rocks give them different densities, which lead to different interactions at plate tectonic boundaries. It's awesome, but let's not get too far off of what we're doing here today. So we've got mafic and felsic, which we can look at as dark or light in color, reflecting the composition of the relative abundance of silica, SiO2, versus magnesium or iron within the minerals of the rock. So we're getting into the chemistry yet again. Felsic, we have intermediate, mafic, and ultramafic. And what I like about this, right, we've got the color, dark to light. We've got silicone and oxygen. We've got magnesium oxide. This could also be used for iron too, right? And the relative proportions of the mineralogy changes. That is what composition is. It is the mineralogy and the relative proportions of the elements that are inside of those rocks. So, whoa, what the heck are we doing here? A description of our 4 types: felsic, intermediate, mafic, ultramafic. But what I like here is ultramafic, silica content, low. Felsic, silica content, high. Iron, magnesium, this one also has calcium. For felsic, low. For ultramafic, high. Temperature at which melting starts. This is interesting, right? The temperature changes because different minerals melt and precipitate at different temperatures. According to Bowen's reaction series, really awesome, slightly outside of our scope today. That's a deeper conversation, but know that igneous rocks have a composition based on the mineralogy of the rocks that form them, which give them different behaviors, and we identify those behaviors by looking not only at the minerals that we can see, but also at the lightness or darkness of that specific igneous rock. So you pick up a rock in the fields, or you break it off of the parent rock and at an outcrop, and what the heck does this tell me? Well, we make inferences about the geologic processes that occurred at the time of formation. Where did it form? How did it cool? What was the tectonic setting? Was it a mountain building event? Was it a basin? Was there water involved? Was it dry? And so if we can start to understand and read the rocks, we can start to, rocks are like, a rock is like a word in a billion, let's say a 4.5 billion page history book. You pick up a rock and you get one word. Now imagine opening up a 4.5 billion page book and reading one word. You would not know the story. But if lots of people spending many years were reading and cataloging individual words, we might start to get an idea of what this story actually is. So learning to read the rocks is learning to decipher our Earth's history. It's pretty fascinating. So here's our classification chart. What do we classify rocks by? Texture and composition. Here's our textures, here's our compositions, and here are our rock names. So step 1, is this rock igneous, metamorphic, or sedimentary? Step 2, what is its texture? So then we say it's igneous. Now, step 2, what is its texture? Step 3, what is its composition? And then I can put a name on it. Phaneritic, felsic. Phaneritic, felsic looks like I'm holding granite in my hands. That is the skill set that you develop as a geologist when you learn to identify rocks. Rocks are cool. Rocks are everywhere. Rocks are important for understanding Earth history. We identify igneous rocks by texture and composition, and those can indicate the environment and the conditions at which those rocks form. Thank you so much. I appreciate your attention, and I will see you again.